All right, so I think we're probably getting towards a quorum here. It's about 10 or 11 minutes past the hour, and there's quite a few people in the room. So let's make a start, I suppose. I do encourage some questions in line. I can see some folks saying hello, hey everybody. I do also, appreciate any questions along the way. I'll try and answer them in line as much as we can. I said at the top, make them hard, but not too hard. So no, do if there's interesting questions or perspectives that people might think would be interesting to kind of handle in line or to look at as the talk goes on, then let's talk about things. I do have quite a few slides to get through. If you see me looking over here in this direction to my left physically, but I'm not sure which way the video is flipped, then that's because I'm cheating. I have an overview of my slide deck here, so I can kind of skip around if there's particular questions that things would come to mind. I have quite a few examples and a few case studies of DPDK APIs. So yeah, let's see. All right, on that note, I'll kick off now. So hello everybody, Haaren is my name. I'm a network software engineer working for Intel. I primarily focus on software optimization, so performance really of software, working quite a bit in DPDK previously, also working in the OVS community. So you may have seen me in that community or active on the OVS mailing list and looking at the path performance there. Ultimately, I'm motivated to always try and extract the most performance we can from the software we write. I think there's a certain beauty or elegance in writing really performant software. And from that perspective, I've been looking at DPDK APIs, and I thought maybe what would be an interesting talk to do today as part of the virtual user space is to discuss what are DPDK APIs looking like today, and particularly from a performance perspective, could we make them even better? Now, I'm saying even better because, as most of us here know, DPDK has been designed primarily around performance, or at least with performance in mind. And as part of that, DPDK APIs are actually very performant, and there's some really good examples of good API design in DPDK. So to jump in, and let's talk quickly about what it is we're going to try and cover. I think we have a 40-minute session today, so I should be ending up at about 10 to the hour. I'll try and leave a bit of space for questions towards the end, in case there are any coming up on the conclusion slide or so. Again, encourage you to ask questions throughout if there is anything you'd like to know about. So first of all, I'll spend probably about 5 or 10 minutes. What is an API and why do we care? So I think most people are probably like, oh, this is the really boring part of a talk, you know, you paint the background. I'd like to frame particular questions in particular ways. So I'm going to talk about APIs just a little bit with an example or two from DPDK. We'll talk about how that API impacts performance. And this is why I wanted to paint the API background first, because there's certain questions and certain ways of looking at an API that I'm going to continue throughout the talk and continue to kind of refer back to. So it helps to set that scene. And then there's a few case studies. That's ultimately where I'd like to spend the bulk of the time, where we investigate certain parts of DPDK and certain packet processing problems or API issues or designs that we can create to maximize performance or to make trade-offs around performance and things like that. And I do have a couple of suggestions for DPDK APIs. I have one or two detailed out quite well with diagrams where I hope that we can at least understand what these API changes that we could make for performance reasons, what they are, and then we can discuss and think about them as a community. But there's also some that are slightly more, let's say, not as tangible, not as solid suggestions that I think are very interesting to think about in terms of how could you make software go faster? But given the current state of the DPDK APIs, I'm not sure if they're good suggestions to actually go and change the code. So look, on that, what is an API and why do we care? Let's get into the bulk of the talk here. So fundamentally, an API is a contract or an interface between two software components. In a way, it's the language that two components talk to each other with. In practice, what that looks like is it's a function prototype. So in the C language, which DPDK is written in, that is usually a function prototype in a header file. Sometimes an inline function in that header file, sometimes a function call or direct function call to get to that and then implement it in a .c file. The function prototype itself influences how this API can be implemented. And what that fundamentally really means is that there's a few things associated with that API. There's arguments being passed into it, there's a return type, and there's certain restrictions around that API. And these restrictions are usually in the form of documentation and are essentially limitations on what you can do with that API. So what is on a good API wish list? If I talk about API design and I talk about what would we like, really we are trying to focus on a number of different things, and you've always got to prioritize these to some degree. So high performance is something we'd like, particularly in DPDK. We want good abstractions, or like encapsulation of certain software components so that the internals aren't visible to everyone. So that's abstraction or encapsulation, whatever term you would like to use. We have modularity so that we can kind of plug in and out various components to make it a modular or kind of extensible API in a way. We'd like it to be usable, so usability is a big concern, particularly as projects grow and develop and get more mature and get more users. These very kind of, I'll say, ninja style APIs with very weird parameters are just kind of awkward and cumbersome to use. So usability. We want simplicity. Simplicity is always a very powerful and useful thing in software, in my opinion. Stability, both in terms of just the API not changing, but also a BI, so application binary interface, ties in here. So these are all things we've talked about at previous user spaces. Pick X of the above, there's always going to be trade-offs. And that's kind of what we can frame this API discussion in today. So looking at, for example, ETH-RX burst, we have port ID, queue ID, RX packets, and NB packets, or a number of packets, as arguments going into this function. We have a return type. It's a static inline function, so it's actually implemented in the header file in this case. And there's certain restrictions around this API. So the documentation does actually show or restrict how you can use this function. So that's just a quick overview of an API in a way. Yes, the keyboard in the background is the new oscilloscope. But that referred back to the previous talk for people who are confused. So look, we talked about the arguments passed in. Those arguments are fundamentally used to implement the functionality behind the API. So if we pass in a pointer, then do you have to dereference that pointer to be able to do something useful at the implementation level of that API? That has a big impact on source code level optimizations. So how you implement an API depends on the arguments being passed in. Seems fairly logical, I think. The return type isn't quite as interesting as the others, so I didn't put it on this slide. The API restrictions, however, or documentation around an API and how it should be used can be very interesting. So it essentially places limitations on the user of the function. And it's really powerful in terms of avoiding complex situations. So for example, the DPDK ETH-RX burst is documented to be not thread safe, instead of the DPDK implementation itself having thread safe access, but also a mutex or something underneath the API. So by documenting that it's invalid to use a particular, like a particular call method, we essentially avoid locks. So the documentation or the API restriction in this case is really a key enabler of performance in the API, even though it's not there in the source code, it's only documented. So how does this API then impact performance? I hinted at it before with this mutex or locking example, but there's more things here. If we look at this arguments being passed in, I'll focus on the two integer arguments at the start, port ID and queue ID. In particular, these are being handed to this ETH-RX burst function, and they're going to access a static array of these RT-ETH devices. So the integer being passed in is going to be basically used to look up an array index in a static array. I think double-clicking the slides makes them go big. So once we have that dev pointer from the static array, we then dereference that to get the data and the RX queues parameter or kind of member of that struct, which we then index by the queue handle. So these two integer IDs that we passed in are actually being used then at the source code level, and they actually have multiple dereferences through memory. And what that means is it's kind of like a pointer chasing or a linked list. So the parameters of this function actually impact the performance quite a lot. In this case, because it's polling, these things are likely to be hot in cache, and because it's actually a static inline, it can be hidden in the function. So there's a lot of thought went into these APIs to make them usable as well as performant. Also, integer parameters allow error checking at the API level. This screenshot is actually slightly modified from the upstream official DPDK release, just for the slide to make it a bit more consumable. So we had a talk quickly there about what that looks like, and I mentioned inlining of a function. And DPDK is in the diagrams here on the left, where we inline this Ethdev Rx function into the application so that where it's being called from, we have the context of the port ID and the queue ID. And that inlining essentially avoids a direct function call like on the right-hand side of the diagram here. So we're trading off performance and ABI stability perhaps because there's now an inline function. The encapsulation or abstraction of this API is slightly weaker because this RT Ethdev struct has to be exposed. However, it does avoid the need for a direct function call from the application into Ethdev and then Ethdev doing a function pointer call into the PMD itself. So there's a performance versus ABI stability or generally kind of, I suppose, encapsulation trade-off is really what I'm trying to say here. And in this case, I think DPDK absolutely made the right call. The performance of that Ethdev Rx function is very critical, and by inlining it, we get more performance and ultimately make the CPU have less work to do per packet, which is a very valuable trait. But from framing the discussion, these are the types of things that we should consider when designing APIs and do consider as well. And DPDK, as I've mentioned before, is a very good candidate for how to do performant API design. So let's look at a case study, and this is where I'll try and spend the next 20 minutes or so in a number of case studies around DPDK. Excuse me. So around DPDK, where things that have happened on the mailing list recently. So in this particular example, where we'll look at the RX or receive side of a PMD, and the mempool get APIs, or particularly the getting mbuffs from the mbuff cache or mempool cache. This particular discussion was around the IAVF driver that's being upstreamed, and in this case, Bruce Richards and Morten Brorup. Apologies if I get the pronunciation of your name wrong, Morten. So this particular discussion, it was about a week and a half ago or so on the mailing list. I saw it and I thought, that's a really interesting candidate for bringing up here and trying to kind of delve a little deeper into what exactly was being optimized and where that performance comes from. There's a link here at the bottom of the slide for the mailing list discussion. So if someone would like to refer to the exact emails that were exchanged there, they're available there. And thanks, Morten and Bruce, for a really interesting email thread, I suppose. Credit where credit's due. So if we talk about that workload where we have a PMD doing a refill of the NIC descriptor ring. So fundamentally, when a NIC wants to DMA packets into the host memory, it needs buffers or mbuffs, some kind of pointer to actually DMA those new packets to, or the packet data to. And the way that the PMD gives those to the NIC is by filling them into the NIC descriptor ring. That's visualized here at the top purple box with arrow number 4 pointing at it. So ultimately, that's what the PMD is trying to do. So the workload here is fill that NIC descriptor ring with valid DMA addresses to put the packets when they're received over the wire. So the flow of that operation at the moment, I've depicted the logical flow, not necessarily the way the code calls through. I think the logical flow is actually mostly directly from Bruce's explanatory email. This shows what is happening, and that's kind of what we're trying to look at, or looking at it from this angle frames the API discussion really nicely, in my opinion. So if we look at number 1 at the bottom, there's a mempool cache, and that keeps mbuffs that have been used on a core locally in recent times local to that cache, local to that CPU thread, or essentially cache local is what I'm trying to say. So from that mempool cache, we're going to extract a number of mbuff pointers, and that's really where we want the packet to be DMA'd by the NIC. So the mempool API has an RT_mempool get bulk function, which will try and extract a number of, like a bulk of mbuffs from the cache, and then puts them somewhere where you give it a pointer to. The way that this is traditionally done is that the software ring for the NIC, so this middle purple box with arrow number 2 pointing at it, the address of that software ring is going to be passed in, and the mempool API is going to place the mbuff pointers in that array software ring. Then later, the PMD will come along and load those mbuff pointers from that software ring, do some processing, and output NIC descriptors. So they're not just raw mbuff pointers anymore, they're now the actual IOVA address that the NIC is going to DMA to. and it will create them in a nick descriptor format. So it's not just a plain pointer anymore either. It's actually a nick descriptor that ends up in the purple nick descriptor ring box arrow 4. So that's fundamentally what's happening. The hazard or the loss of performance in this particular setup is that, as kind of indicated here by the red X on the right-hand side, is that the loads in step 3, so where we're loading data from the software ring, are dependent or must be done after the stores in step 2. So the mempool API is storing data to a software ring, and later that same data is being reloaded at step 3. And those loads and those stores are essentially loading the same data. So first it's being stored and then it's being reloaded. That sounds a bit like duplicate work, and indeed that's exactly what I'd like to describe it as. So that's a hazard in the CPU, and we'd like to not do this. CPUs do have a feature known as store to load forwarding to try and work around this. So it's not a terrible thing. CPU designers are very aware that this is a common occurrence in general code, but from a performance perspective, it's not ideal. So what am I suggesting? Or rather, what was the patch set that was sent to the mailing list suggested? What did it do? So how it worked is it basically removed some of the mempool APIs, bypassing it and doing the load from the cache directly at the Ethdev PMD. And in a way, we can consider this as bypassing the mempool cache API. We can consider it as reaching into the implementation of the cache and directly pulling data from the cache and using it. But what we see is that step 3 has gone missing. So this particular part where we have to reload the data no longer exists. So by bypassing a particular API, we've optimized this store to load forwarding that I mentioned before was not a great thing for CPU performance in general. And from an API discussion, I think it's interesting as we're kind of blurring this as a trade-off between performance and abstraction. By removing some of the encapsulation and by not using this get bulk mempool API, we actually get more performance because we only have to load the data once. So I thought that was a very interesting kind of small way to look at APIs and performance and optimizations. That's real world, that's relevant, and a recent occurrence on the DPDK mailing list. So if we move on to a second case study, we can consider DPDK Eventdev enqueue. So not Ethdev in this case, but Eventdev. The same concepts apply. I'm a little more familiar with the Eventdev, so I chose the Eventdev here as the method to diagram out and really try and show what these CPU hazards that I'm talking about are. In particular, I'd like to talk about cross-API CPU hazards. So quite often we design an API and we optimize everything under it or above it, like at the application level, but we don't consider the interaction between those two very often, and that's what I'd like to focus on here for a few slides. So this is a micro benchmark. It shows a workload quite like Eventdev enqueue, as if the PMD is loading some data and going to process it. And the two screenshots we have here are perf_top, so a common Linux tool for measuring performance, using something called a feature called LBR, or latest branch records, the -b flag for those familiar with perf_top or perf_record. And that gives us this number here at the bottom where it tells us how many cycles something took. So the two yellow lines here have a number in the middle. There's 4 and 16. What that actually implies is the exact number of cycles that this code snippet took. You'll notice the code is exactly identical. I didn't even recompile it. It's just running twice, once with different code beforehand and once with two different sets of code beforehand. And we notice that there's a performance delta of 4x. So in one time it ran in 4 cycles, the other time it ran in 16 cycles. So something is different, but our code is identical. That's kind of a case where we need to consider these cross-API micro kind of, or CPU hazards really is what I'm trying to say. For those who saw my previous slide on the load store forwarding, you're probably quite aware that indeed this is loads blocked on store forwarding. So I've measured the event here. It's about 5,800 in this first run, the fast run with 4 cycles. And there's, I think that's 400 million in the second run. That's about 70,000x increase of that particular event. 5,000 is in the noise, and this 400 million is very much not in the noise. So we can see that the cause of this performance delta is actually just loads to store forwarding. Now, what does that really mean? Because if we look at it back from an API perspective now, previously we were just talking about CPU performance. Now we're back to kind of API angle of that CPU performance. On the left, we have the slow case. And the application performs 2 stores, one of like uint64 or U64 for short, of a payload and of a metadata. And the event gets loaded by the PMD as a single 128-bit load. And what that means is that's a particular type of load that is loading multiple smaller stores. That cannot forward, or at least not on most modern CPU architectures, definitely on x86, 64. There's a software optimization manual, or SDM, it's often referred to, the software developer manual, that has a really good section on exactly what store-to-load forwarding is and isn't capable of. If you're not quite familiar with exactly what can forward and what can't, there's a good graph. It's really well explained. So I'd encourage you to look that up. Intel SDM, you'll find the download page. If someone wants to pop the link in the chat window, that would be fantastic, actually. On the right-hand side, we have another application. It's actually doing the same work fundamentally, but now it's doing a single 128-bit store, so an SSE register being stored in one go, and that exact same address is then being loaded again by the PMD. So while before I was advocating against doing that in the NIC RX and in the mempool cache case, sometimes when there's an API in between, we don't have another choice. So because the previous example with NIC RX was inline, we could actually fold away the stores and the reloads of that same data. In this case, because we're crossing an API boundary, that's not really possible. The compiler isn't able to do that without all sorts of trickery that we don't want to get into. So what we can do in this case is provide stores that can easily be forwarded to the PMD. So by doing larger stores where one whole event is being stored at a time, we make the performance higher for the PMD underneath. And not just a bit higher, we saw 4x performance delta on a very small micro benchmark, right? I'm not advocating that all your PMD is going to run 4x faster. But we do see that there's a significant cycle difference here in doing some very trivial XOR processing of a bunch of essentially RTE events. And that's significant. We could lose a lot of cycles here if we don't pay attention to these types of cross API CPU hazards. So lastly, let's have a look at the Eventdev enqueue. It's the same component as I just spoke about, but in this case, let's look more on the PMD side where we're loading the events from the application. In particular, the angle I'm looking at it from here is from an unknown buffer size read. So when the application is storing events, it's going to store from 0, or from 1 rather, up to any number of events that it likes. And then it's going to call the DPDK Eventdev API and say, hey, I have enqueued n, and let's assume n is equal to 3 just for these examples on the slides. That's a nice small number to graph and still be somewhat readable. And then we're going to call the DPDK Eventdev enqueue API, and we're going to make the PMD handle those events. So fundamentally, when we call this API with n equals 3, it means that the first 3 events in this RTE event array are valid. It doesn't actually state anything about the ones afterwards. They could exist, they could not exist. In this case, the application has indicated it would not like them to be processed because we said that we had 3 events to be processed. But we didn't say anything else, really the state of that memory there. So in our case today, what happens? The application stores these 3 events, and then the PMD is going to load those events. But the PMD doesn't know how many events are available. The application knew that and passed it as a parameter. So the PMD can find out how many of these events are available for processing by actually checking a runtime argument, or essentially a parameter or argument passed to this function. What that means is that we need to handle anything from 0 up to n, and roughly arbitrary number of events, usually 32, possibly 64, possibly even more. Technically, the API doesn't state an upper bound or a max or a min. So from 0 or 1 up to n events. And what that means is, from a software perspective point of view, when we need to load that data, we end up with a loop kind of like the below. I've kind of abbreviated the SIMD registers here to SIMD_EVS or events. I didn't want to type out a bunch of SIMD code because it might be a little tough to read, but fundamentally consider this loop to be loading from the stack the events that the application has provided and loading them into SSE registers or SIMD registers for further processing. Now, the problem in this case, or problem from a performance perspective at least, is that it's unsure of if the PMD, or if the application has written a whole bunch of events, so did we get 32 of them, for example, or did we only get one? And the reason that becomes a problem and demands this loop like we have where we iterate from 0 to less than the number of events is on my next slide. So I'll talk a little more here. So why do we care? Why am I looking at this? And it's because the variable n number of loads actually loses us some performance. So that n depends on the burst size that the application provided. N equals 3 from the first slide. So in this case, there's 3 events. But flat code, as in code that just runs, there's no loops, is often the fastest. However, this burst size isn't predictable. So we don't know, and today our PMDs do not have a way of optimizing against that value n. However, we do know from a micro benchmarking point of view that blindly loading events is faster. Even if there's a constant burst size, so bursts are always 8 or 16 or 32, blindly loading them is still faster, just purely because there's no loop in the way. But is it valid to actually go and do that? Can we just blindly load 4 or 8 events from this array and then go and process them? The answer is unfortunately no, not today. So if the PMD was to blindly load these events, we would get all sorts of nasty things like buffer overflows, seg faults. On the diagram here, I've presented a case where we have 3 events, and the 4th event could be on the next page, so a 4K page or a 2 meg huge page, it doesn't really matter. But if we access that page and it's not mapped to our virtual address space, we're going to seg fault. So reading past the application provided buffer is definitely not a good idea. It is invalid, it's not correct, and correctness trumps everything else here. So the application buffer has an unknown size except for this n parameter in the API. And that's really limiting us in this case, because otherwise we could blindly load more data. Thank you, Kev, for the SDM link. So how can we improve DPDK APIs for more performance? Essentially, I'm going to answer the question we posed previously. How can we enable the PMD to load more data blindly, or I say blindly in quotes, in a way such that it doesn't have to be very, very careful about not issuing one load too many. That's really what I'm trying to say. So we could add a function parameter. So this goes back to our API design. We can add more context or more information in the API or the function header itself and state the buffer size. So an application could say, hey, I have a buffer size of 8, but I have 3 events in that buffer that I want you to go and process. So that would allow the PMD to then do a branch, essentially an if or a switch, on that value. And we could blindly load up to that value. So, and that value will always be greater than or equal to the number of events. So if we have 3 events, that could be possibly 4 or 3, or much larger, it could be 32. And in theory, if the application or the PMD wanted, we could load more data than we were actually going to process. And I've indicated that here with the kind of red outlined event with the red X through the middle, that it is loaded data, but the PMD is not actually going to use it. It's not going to send it to the Eventdev or to the NIC to go and actually be processed, but it is allowed to load that data now validly. It is correct to load that data and just not do anything with it. And that kind of makes our code a little simpler in terms of the PMD for our performance, purely because we don't need to be aware of loading exactly the right amount of events anymore. We can overshoot a little and then just not process that in SIMD later on. And that actually has quite a significant delta or performance difference. So moving on, there's another solution, of course. We could have an API to commit to a buffer size, where an application calls, hey, I know I will always call you with a buffer size of 4, and we could specialize the Eventdev enqueue function of the PMD. So in this case, we've added more code to handle that use case. We can see at the bottom here, we have Eventdev enqueue, the specialization for buffer size equals 4. And the PMD could pick at initialization time, for example, which function pointer should be used for that particular, for that enqueue, for that application. If the application chooses to not commit to a buffer size, it will use the previous version, which is a little slower. And if the application wants ultimate performance and has a fixed buffer size and it can communicate that to DPDK, then DPDK can optimize against that property that we now know of this API, or particularly this exact instance of that API. And we could use a different function pointer. We could also branch on a flag. There's a number of ways to implement the exact IP in like instruction pointer movement, but a function pointer would be and with function specialization would be one solution to that. Yes, exactly, Natalie. It sounds like C++ template specialization done manually. You don't need to do it manually. You can still have the compiler do it for you, even in C code. I think actually last year's user space presentation that I done was on that exact topic. So if you're interested in that, definitely go have a look. The compiler will do all the hard work for you. We just need to give it constants to propagate through a static inline function. That's basically how it works. Moving swiftly on. Isn't LTO a solution to most of these problems? It is, but only if the linking is actually done in a way that the application, or rather the linker, can be aware of the context. And in this case, I'm not sure if an application will call with a burst size of 4, will the LTO be smart enough to figure out it can use a different version of a function? In theory, I think it might be possible, yes. I don't know if many people actually use LTO in practice. If you do, please drop in a comment. I'd be very curious to learn about how much it gains your particular performance, and maybe drop me an email as well if you'd like to continue that discussion afterwards or after this user space. Interesting suggestion, Tom. Thanks. So lastly, there's another solution, of course, which kind of goes back to the 3 points we had at the start of the slide, where we can limit the APIs through documentation or through restrictions. And we could just say, hey, if you want to enqueue into Eventdev, you must provide at least multiples of buffer size X. In this case, you can see there's no code changes required. We don't need to do function specialization. We don't need to change or break our API, or API in that case. But we are adding limitations. So it is actually kind of an API break in a way, in the let's say, technically correct way, in that the API actually changes, but we're now making assumptions that weren't there before. And that is kind of an API break as well. So I'm not suggesting that we go and just blindly change this across DPDK. We can't do that. It would need to be communicated, possibly have a different function name. As long as each Eventdev doesn't require a different size. Very good observation, Stephen Heminger, thanks. Indeed. I think the sweet spot is probably around 4 or 8 events. And the reason for that is quite simple, that we can load them into SIMD registers, do a transpose, so to get all of, in particularly the metadata of the event into one SIMD register, and operate on 4 events in parallel using, for example, SSE or AVX. So there is a sweet spot here, kind of like DPDK's burst size is often said to be a sweet spot of 32 or 16, depending on your use case. Indeed, Morten, you say 4 might be a good baseline now, but what in 4 years? True, we can always try and revisit those kind of things. This is a suggestion, and absolutely, this kind of feedback is fantastic. So thanks for that. I think let's open a discussion around if this is something that we think DPDK should be looking into, or if this is something we'd like to do. There is definitely potential for performance gain here if we do this, but is it worth this squeeze? Do we need to be careful to not have too much? I saw a reference on a mailing list recently as to micro optimizations or so in APIs. Is that possibly something that we're suffering from here? I don't know. Let's discuss that. I see another comment from Luca. Definitely a break and a smiley face. Absolutely agreed, Luca. John Alexander, aren't these microarchitecture optimizations best left to the compiler? Often, yes, in certain ways, but at the API level, it's very difficult for a compiler to optimize. So take an example where we compile DPDK into a .deb or into a .rpm, and then that version of DPDK is going to be used and linked against by multiple applications. That's now in a shared object, so we can't have the compiler micro-optimize that for a particular use case. The compiler isn't even aware of what application is going to be calling it. Kind of refers back to the LTO issue back from earlier, that it's, you would need to statically link is kind of what I'm saying, or at least that would help in this particular case. So yes, Bruce, you have a good point here, that a constant parameter that the compiler can resolve at compile time into optimized code is good on all architectures, absolutely. And that's actually what is being suggested here on the previous slide, where we have this specialization of the Eventdev enqueue with a particular buffer size. And looking at this again, Stephen, I see that this is kind of the point you're making, that we need to make sure the burst sizes are the same for each PMD, and very good point, yes. Yes, Ray, you mentioned a good point, that we could switch on the value of n, and when n is greater than 4, then always use 4. Constrain roughly a similar comment of you can branch on num if greater than x inside your function. Agreed. So these are the kind of things that we can investigate and essentially put inside the PMD. Duff's device is one of the other tricks we can use to kind of do this loop unrolling of loads. The point is still always that what we want to do is blindly load or you know, in sequence, in flat code, load a whole bunch of events in one go. Other things that we can consider, if we go back to I think the first or second case study where we have load store forwarding, is can we communicate perhaps that API is going to be using, or the application is going to be using a large store. So what we didn't really talk about in terms of API design yet today is that the PMD today wants to load, let's say, 128 bits at a time. But based on the application, it may or may not be the most performant way to do that. So the PMD might be better to load 2 uint64s and put them into an SSE register itself if the application is storing them as 2 uint64s. If the application is storing as one large store, however, it's much more performant to load in one single load. So there's a number of angles here around loading of events and the exact microarchitectural things around that do have a significant impact on performance. And in particular, if an application is seeing lower PMD performance than expected, then that cross API hazard, in a way, moving from the application through the DPDK API into the PMD, depending on what the PMD implementation is kind of an interesting area to look at how the performance goes from a microarchitectural level through that. So a few questions here I see. For a non-burst variant, we're using const and have 2 function pointer already. Jaren, yeah, very good point. So the Eventdev APIs themselves, if you're only enqueuing a single event, we do have a separate function pointer for that allows the PMD to not handle loops inside in the code, which quite simplifies the amount of essentially looping code in the PMD. So yeah, very good point. And we have some specializations as well. If you're only enqueuing new events into the Eventdev API, or only forwards, or only of a specific type. So again, that allows compile time specialization of the PMD, and they're things that I'm quite fond of actually at the moment. So does the events be of the same type, mbuff, timer, etc.? Yes, in this case, what we're talking about is just processing the RTE event structure into, like loading them into SSE registers or some kind of SIMD registers. And what that really means is we're about to start processing them. So the exact type of event and the flow ID or the various properties, operation type, schedule type that the event have at this point don't have a context yet. So depending on what processing is required for the PMD, this will be a different amount or different processing and different things. So if there's more questions, feel free to ask them. In the meantime, I hope this was of interest for you and that it maybe gave some insight into what API design can look like and what tweaks we can still make in DPDK APIs to go even faster. Thanks everyone for the comments and the interactive discussion. Very, very nice. Feels a little like a real user space hallway track, despite we're all in separate geographic locations, of course. One comment here from Jaren, that similar constraints for TX burst as well. Indeed, there's a very similar analogy we can draw on not the enqueue to the Eventdev, but the TX side. Particularly on the storing of data as well, because we have that same buffer size kind of limitation, but we are past the parameter saying how big the array is in that case, because the application actually needs to know how many mbuffs we can receive in total. So yeah, these are all things that we can consider, and we did focus on the Eventdev API for this discussion, but it applies kind of across the board, and actually for most of packet processing as well as DPDK. So long as they're burst-oriented APIs, then this pretty much applies. All right, thanks folks. Could you dynamically allocate or reallocate RTE event arrays as they're added and just blindly load? It would imply copying them, Brendan. So if you want to reallocate, you're essentially saying allocate again a bigger thing and copy them, and by copying them, we've already loaded them, which is kind of the work we were trying to do in the first place. So at that point, we've paid the cost already, and I'm not sure how much we'd gain from that reallocation. Interesting concept though. Cheers, folks. All right, I'll leave it there. I'm at time. very interesting discussion. Thank you again for all the comments. We look forward to continuing the discussion and enjoy the next talks.